Hello, this is Dr. Viv. In this video, I will show you how Euler's formula can be used to evaluate pretty complicated integrals. Now, the two integrals that I've shown you here are common in signal processing, and they have a combination of the exponential and trigonometric functions. There are more complicated integrals in that same field, but these are the most basic ones. If you were to solve this using the techniques of calculus, I believe the right way to do this is use integration by parts. But if you use integration by parts on sine, you end up with cosine, and then you have to do another integration by parts to end up with sine again, and then you shift all the integrals involving sine to one side, and it takes about half a page, maybe even a page, to do this properly with success. And then if you had cosine instead of sine, you'd have to repeat the process all over again. I will show you a way of doing these integrals in just 2 lines, and as a payoff you'll get to do both sine and cosine with the same amount of effort. So that's the power of Euler's great formula. Let's recall what that is. It is e to the I theta is equal to cosine theta plus I sine theta. In my earlier video, I showed you how this formula came about by simply considering the exponential function and substituting I theta for it. This formula can actually be used to solve these two integrals in the following manner. I will start by writing I as our required integral. Let me start with the left one. This I'll just get later. So I'll write I as e to the ax sine bx dx. This is the imaginary part of the integral e to the ax times e to the I bx. Because remember, using Euler's formula, e to the I theta has got the real part cosine theta and the imaginary parts sine theta, and the I just comes along for the ride. So this is called the real part and this is called the imaginary part of a complex number. And therefore I've written sine bx as the imaginary part of e to the I bx. That's all I've done here. Now this integral, however, is not very difficult to evaluate because this is just using the property of exponentials, e to the a plus ib times x dx. Now that is the integral of an exponential function. It can be very simply performed. Integral e to the some constant times x is 1 over that constant times the same exponential. I've just got to be careful to keep putting imaginary till I'm done. Now there's also going to be plus c, the constants, so I'll call this constant plus c, and just to make sure that it's a complex number, I'll put a quote around it to show you that it's a complex number. It's a complex constant. So I'll expand the complex constant later. I'll expand this quote c as c1 plus ic2. In other words, I'll write the complex constant as a real constant plus I times the imaginary part of that constant. So for now, I'll just indicate it by quote c so it doesn't come in my way. Now the main problem with this calculation is to find the imaginary part of 1 over a complex number. Now you can use a process similar to finding the form of a square root. If you have a square root in the denominator, you rationalize it by multiplying it by the complex, the conjugate square root. In the same way, you have to make this come to the numerator by using the complex conjugate. Now last time, in the previous video, I introduced the complex conjugate of a complex number. If I have z equals a plus ib, then z bar is a minus ib. So the complex conjugate of a plus ib is a minus ib. So what I'll do is I'll write 1 over a plus ib as a minus ib divided by a plus ib times a minus ib. All I'm doing here is multiplying and dividing by the same thing, so it's nothing illegal. And when I multiply through in the denominator, the numerator stays the same. The denominator, I'm going to get a squared, and then I have plus iab minus iab. Now be careful here. This is ib times minus ib. So I'm going to get a minus I squared. But I squared is minus 1 because I is equal to the square root of minus 1. As a result, negative I squared will be plus 1. So this is just plus b squared. These two terms cancel out, and I end up with the result that 1 over a plus ib is a minus ib divided by a squared plus b squared. Now if you do this result 1 or 2 times, it'll become second nature to you, and these computations would not have to be done every single time. So the utility of this Euler's method depends on knowing results like this after a while. So you don't do them again every single time. So once you have those results memorized, you're going to get 1 over a squared plus b squared. Since that's a real number, I'll pull it outside, and then I'm just left with the imaginary part of a minus ib times e to the a plus ib x plus the complex constant c. Now this can be written as 1 over a squared plus b squared times the imaginary part of, let's expand this, e to the a plus ibx. I can rewind what I did here and bring it back to this form. So e to the ax, which by the way is real, can be also brought outside the imaginary operator, and I'm just left with a minus ib times this part, e to the ibx. But I can again rewind that using Euler's formula. So that's just cosine bx plus I sine bx. Now it's a matter of multiplying. So I'm going to get e to the ax divided by a squared plus b squared. Let me just simply multiply everything first and then take the imaginary part. So that's going to be a cosine bx. Now minus I and plus I will lead to plus 1 because minus I squared would be plus 1. So I'm going to get plus let's see. So this is going to be plus b times sine bx. The next term is going to be, I've done this and I've done that. Then I have to do this. So I'll get plus ia sine bx. And then minus ib cosine bx. So I've basically written this as a product of a sum of 4 terms. The imaginary part I can now do. So the integral that we started out with is the imaginary part of all this. So that's just e to the ix over a squared plus b squared times, imaginary part means anything multiplying an I, and those two things have an I multiplying them. So that's going to be a sine bx. Oh, don't forget, the imaginary part of the constant c I'll just write as c2. Minus b cosine bx plus c2. The big payoff is that it's not very difficult to find the real part. I just leave out those two and write these two. So I've also found the integral e to the ax cosine bx That's going to be e to the ax divided by a squared plus b squared. And the real part is just these two terms, so I'll write those instead. A cosine bx plus b sine bx. And this time I'll keep the real part of the constant, so it's plus c1. So in this way we have actually solved two pretty substantial integrals. If you try these by integration by parts, and I would like to encourage you to do this. So if you have time, try these by integration by parts. I'll abbreviate integration by parts as IBP in this video course. So if you do this using integration by parts, you will find that each of these will take at least a page, and it involves all kinds of trickery to get this a squared plus b squared down there. So it's pretty not very easy at all. So this way Euler is able to get both the integrals in one go. So that I like to say it's 400% more efficient to use Euler. Now you can also, like I said, this is not the only signal processing integral that you're going to get. There are some more complicated signal integrals, and here's an example of one. If I have integral of some power of x to the n, e to the ax sine bx dx. Now this is totally out of the range of integration by parts. You'll be sitting there doing this all day. So what you would do instead is write this as the imaginary part of integral x to the n e to the a plus ib times x, and that's a lot more manageable because this looks like the integral of x to the n e to the alpha x dx. Now for if the n value is really high, you can break it down by using recursion formulas. So you would use recursion formulas here. And you'll reduce it to lower powers of n, x to the n minus 1, e to the alpha x, and so on. All the way to finally you'll get e to the alpha x. I've called alpha equals a plus ib here. And once you break it down to these, you can evaluate each one separately using the same Euler trick that I taught you. And then you can finally get the full form of this scary looking integral. The reason these integrals are useful to do in algebraic form like this is because you can test the limits. You can say a goes to infinity, b goes to something, and find out how the signal behaves as different limits are approached. Of course, you can take all this and stick it into a computer or Wolfram Alpha, but that would be no fun, would it?